Hello everyone, welcome to this video. In this video lecture, we are going to learn about the principles associated with quicksort. In the previous two videos, we learned about the insertion sort, then we learned about the merge sort. Now in this algorithm, we are going to learn about the quicksort. Okay, so these are the different things that we are going to cover in this particular video, starting with the algorithm, some example, the complexity, known space and time complexity, and the properties. So these things we have covered for the merge sort. Now we do for the quick sort also. Now this is the algorithm for the quick sort. Now the insertion sort, we talked about the insertion sort was a iterative algorithm. The merge sort was a recursive algorithm, and this is also a recursive algorithm. And now how can we say a algorithm is a recursive algorithm or an iterative algorithm? Recursive in the sense that it calls the same function again and again until that particular task is not completed. So recursive in the sense same function has been called. So same function has been called by the same the main function itself. The same function called until the task has been completed. So since the same function has been called, so this is known as the recursive type of algorithm. And partition in the sense it will just divide and go on. And this also fall under the category of divide and conquer. So the previous marshal is also on divide and conquer. This is also on the same line, divide and conquer. So this falls under divide and conquer. So this is a recursive algorithm and this falls under divide and conquer. Now, previously we talked about one merge sort. There is let's start with the initial one. There is a quick sort which is taking three parameters. This is the array, this is the starting index, this is the end index. We have some conditions. If the condition is fulfilled, then we follow this particular three steps. In the first step, we call another function known as partition, which takes three inputs, same as what is going to the quick sort. There is the array, starting index, ending index, and it returns z, and it's an integer. It returns an integer. Then based on a particular integer, it calls the quicksort twice. First it will call quicksort from the starting index to that particular integer minus 1. Then it will call into the next part, that is the second part of the where it's the next part to the end of the array. So if suppose for example, if we have an array, let's suppose we have an array of, it starts with 1, middle point is 5, that's it, and 10. Suppose, I'm not saying it is m and it is n definitely, but let's say, okay, this is n, this is n, and let's say, okay, I don't take it for confusion because it might not be taken as middle point. Let's say z is something in z equal to, let's say, uh, 7. Okay, z somewhere it is here z. Let's say I'll talk about this what partition I'm going to do. So what does quicksort does is that, let's say this is 7, then it again quicksort to this 1 to 6, and again quicksort to 8 to 10. This is how this part. So this part is called to this part, and the second part is called to this. So this is how the algorithm looks like. So basically, this is the overall idea of the how the main part of quicksort is. But now we'll divide it to more depth parts. So I will talk each and every part. So as the heart of the merge sort was some another algorithm. So this is also how the heart of the quicksort, or the core part of the quicksort, is the partition algorithm. Yeah, you have merge algorithm, you have the partition algorithm of it. So based on, because it's just the index has been passed every time this partition algorithm has been called. So we talked about first what is the partition algorithm is all about. Okay. Now this is the partition algorithm. This is a pseudocode of the partition algorithm that we are going to talk. Now it also it takes an array A with starting index and the end index. Then the end index is placed down into some numbers. Then it takes a value I. Then there are some conditions that get uh, uh, that the conditions are there based on a for loop. This for loop runs, and the for loop some conditions are there. If the condition is satisfied, then this will happen. Or if else part is that, if else, then nothing will happen. It will just go to the j equal to 2, or just the next n plus 1. Once the for loops get completed, then there is again some operations are done, and at the end it returns I plus 1. Okay. And interchange AI with AJ means if we have, let's say AI is equal to 4 and AJ is equal to 10. Interchange in the sense, after interchange, what will happen? AI becomes 10 and AJ becomes 4. This is the form of interchange that we are referring to. Okay. So this is the overall algorithm part of it. But to understand more clearly about the algorithm, I think an example is more suitable for it. So let's go to an example of it. So this is the algorithm that we are referring to. This is the algorithm that we are referring to, and this is an example through which we can understand more clearly. Uh, let's, as we done for the merge sort, I will just give an defined example to understand it. Then I'll come back to the algorithmic part of it. Okay. Uh, as we're talking, we talk about the partition algorithm. So let's talk about a partition algorithm now. Let's take an example of an array. Let's say there are how many? Let's say there are 7 elements. We take an array of, let's say we take an array of 7 elements. 1, 2, 3, 4, 5, 6, 7. Okay. That's any random numbers between one, let's say 3, 6, 9, 2, 1, 7, 5. Any random numbers we take. It's an array. So since it's an array, now let's have the starting positions. Let's define I and j here. This is 5. 5. Now, what is m? And the array starts from here. It is 1, 2, 3, 4, 5, 6, 7. So these are the indices. These are the indices that we are referring. Okay. Now, moving forward to, okay, now define some I and j here. Let's define here m is 1 and n is 7. Okay. Now let's define indices I, which is 0, and define j, which is 1. So I is 0, j is 1. Okay. Now let's do one thing. We save this number. What we do? We initially save this number with the last number. Let's say we took this number itself, the last number we took as a reference. Okay. The first shot, let's say the last number that we took, we store it in a temporary variable. Let's say we store it in z, a of n. Okay, so what will happen? A of n is actually equal to 5. Okay, so this number, the last number we are storing is 5. Now we define j, we define I, and mn now get complete. Now what will happen? We will move j from this particular position until here. So j will iterate to this position. So j will move from 1 to till 6. It will move. Okay. Now in each of the part, what j will do, it will try to find out whether, let's say, a of j is less than equal to z. Okay. And if that condition is true, then something will happen. Then what will happen? If this condition will true, first I will be incremented, and then the a of I and a of j will get interchanged between them. If this condition is true. If this condition is true, then this will happen. Or else j will be just incremented if this is not happening. Okay. Now let's see. First of all, okay, then we first found 3. So first j is equal to 1. So here what we see is 3 is less than 5. So that means I will be now incremented. I will be I plus 1. So I will be 1 since I initially was 0. I was 0. So I will be 1. And what will happen? A of I and A of j will get interchange. That means a of 1 will get interchanged with a of 1. So it will not just, it will, what will happen, the values remain the same, but now this I will become 1. I will become 1. Okay. Then we have now another array. Let's see. We have an array now again here. Here 3. Since there is no change of part, 2, 1, 7, and 5. Okay. And j will be incremented. Now j will be here and I will be here. Okay. Now when j equal to 2, z is the same. Z is not changing anywhere in between. Now j equal to 2. Now 6 is not less than 5. 6 is less than 5. This is not true. So simply j will get incremented. Now j will be equal to 3. That is 2 plus 1. Okay. Now when j equal to 3, this will happen as this. So this is 3. I still is here. This is 6, 9, 2, 1, 7, and 5. Now j will be here. This is j equal to 3. Now for j equal to 3, since again 9 is not equal to 5, this is not true. So simply j get incremented. This is 3 plus 1. So here 3, I still the same. 6, 9, 2, 1, 7, 5. Now j will be here. J equal to 4. This will be here. Now for j equal to 4, what will happen? Now we'll check 2 is less than 5. This is true. Now what will happen? I will get incremented. Now I plus 1. So I was initially 1. Now I will be 2. Now since I will be 2, so I will move from here to here. I will move to here. And the next phase is what? A of I will get changed to A of j. This get interchanged. This get interchanged. So 2 will move this part. Yeah, 2 will move to here and 6 will move to here. So after changing, what will happen? 3 is here, 9 is here, 1, 7, 5. So in this place, the 6 will come. In this place, the 2 will come. Okay, these are the changes that happen. And I remains here. And after this step is over. Now j will move to here, which is j equal to 5. Okay. Now for j equal to 5, we get this particular input. Now for j equal to 5, we took 1. 1 is less than 5. This is again true. I will get incremented. Now I will be 3. Now this 2 will be swept. This part and this 2 will be swept. So after swapping, how it will look like? It is 3. It is 2. It is 6. It is 7. And it is 5. Okay. Yeah. After swapping, what will happen? Small to accommodate 9. Okay, since these two will be swept, now 1 will come to this place and 9 will come to this place, and now 1 will come to this, so I gets incremented in the previous step, so I becomes 1 and j becomes this. Now since this is over, we move to the next one. J equal to 6, 7 is less than 5, this is not true, and this gets over. For this particular loop, as I said, j will move from this part to this part. So in the sense, j will move from m to n minus of 1. If this is m, this is n, it's m to m minus 1. And this whole thing will run for it. Okay. After getting this, what we will do, since this running is over, now the last step is what? We'll increment j. We will increment I. I will increment it since this phase is over, and then we'll we'll do again one interchange. What interchange we'll do? We'll interchange a of I with a of n, or simply termed as z. What we will do? So at the last part, what will happen? We have this particular input of array. When it finishes, it has this 6, 9, 7, and this is 5. And where I is standing? Right now I is standing on this particular position. Yeah, I is standing in this particular position, and this is the position where a of n is happening. So this particular position will be swept, interchange. So now this will be 3, this will be 2, this will be 6, this will be 9, 7. Now what will happen? I plus 1 happens, so I is not this now. I was that previously. Now I plus 1, so I move to I moves here. I moves here. Now then there will be swapping. After plus 1, then there will be swapping. What will happen? 5 will move to here. Swapping between these two parts. So 5 will move to here, 6 will move to there. So 6 is comes here and 5 moves here. This is the final part. After running for one iteration. One iteration in the sense when there is an array and the input of the array was partition algorithm, and partition what it was getting, it is getting an array of size m and n. So it gets an array of this an array, and size of m and n. So initially what was there? 3, 6, 9, 2, 1, 7, and finally what it got at the end of it, what it got? 1, 2, 3, 4, 5, 6. So 1, 2, 1, 2, 3, 4, 5, 6, 7. Okay. Finally we got 3, 2, 1, 5, 9, 7, 6. 3, 2, 1. I will write this as different color. 5. Okay. 3, 2, 1, 5. 3, 2, 1, 5, 9, 7, 6. 9, 7, 6. This is the output that we are getting from this. This was the input of it, and this is the output from this particular part. And at the end, what you will send, we have a z value that we are referring, and z value is this particular value. So what you will send z will be at the end, that will happen. So we'll send z is equal to 1, 2, 3, 4. So z will send this 4. So that particular position I equal to 1 we will send. So let's recap what we are doing here. And if you see some particular properties, if you say this here, there is a particular property associated with this final input. So here, whatever value we have chosen in the initial part, it may be the last, it can be the middle, it can be anywhere. For simplicity, I've chosen the last number. It can be the first number also, it can be any middle number also. But whatever value we have chosen as the z, and this is also known as the pivot part, what we in technical terms we name as a pivot. So whatever element we choose as pivot, after this whole partition algorithm runs, the pivot element will be in such a place that all the values in the left side will be less than 5, and all the values at the right side will be greater than 5. You can see this. So all the values less than 5 are this, all the values greater than 5 are this. But mind you, this left and right array are not sorted. Left and right subparts are not sorted, but they are less than a greater than, but they are not sorted. Here it seems like sorted 976, but the example seems like 976, but you can see the left part. So it might happen coincidentally, but generally the left and right parts are not sorted after the partition algorithm does so, but at least we get the particular position where you can say the left and right part, if you see that particular positions are sorted. Now, so we'll take a full example of it, then we'll get it. But this is the core idea of partition. So we will take a particular element from one part, we compare it. Whenever we find an element which is less than this, then we'll swap. So whenever we find an element which is less than that, we just increment I and then swap of it. Now let's say we don't increment I and swap, what will happen? Just think of it. If we don't increment I and we generally swap it, just swap. In the first thing we see, that first of all, if we don't just swap it, this 3 value get garbage. So generally, array is what is a stack of memory locations that are being stored. If we talk about a computer, actually it is a memory location. So it's not that we take an array of size 10. When we take array, we just took an array of size equal to 10. So what will happen in the memory, let's say in the CPU or in the memory, whatever where we have the memory, let's say RAM with the memory located or a secondary RAM, we have a stack of memory addresses. So from that memory addresses, 10 locations are given to us, and these locations addresses are mapped down to an array for visualization. But it's not that the above 10 or below 10 are not there. Some values are there, which if we have flushed out, we have make 0, then 0 can be there any other value. But it might be some values are there, some garbage values can also be there. So if we have swept without initially I was 0, as I told initially I was 0. So if we have swept without incrementing I, if we have swept it, that this number will get lost. It will get to somewhere and some garbage value might be here. This is the first thing. Second thing, the condition that I said, the all the numbers left of it should be less than and the right of it should be greater than this, that might not be true. Let's say here 2 is greater than equal to 5. When j equal to 3, I equal to here. If I have not incremented I, j, then that particular thing will not be here. So that particular condition will not be get increment incorporated on this particular algorithm. So to have this left hand side right hand side part on place, so we keep this I equal to I plus 1. So initially I was 1. So let's say we have 3, we have 6, we have 9, 2, 1, 7 and 5. Now when I equal to 1 and here j is equal to 4. So 1, 2, 3, 4. Okay. Now let's say this was the part that need to be here. 6 and 2 need to be interchanged, but let's say we interchange 2 and 3. Okay. We interchange 2 and 3 and now we have 2 here and then we get what? 6, 9, 1, 7, 5. Okay. And we get 2 here since 3 and this 2. Okay. 2 gets here, 3 gets here. So you can clearly see these things, and if you just see upon this, what happens 3 and 2, 6 and 9. So whenever we place the j position, whenever we place an I position, so whatever the I is there, that is less than, whenever this I is there, so whatever position is I is taking down, that particular position is less than equal to 5. In everywhere, if you see I less than equal to 5, if you see I after interchanging, I becomes this, so this is become less than equal to 5. So whenever I is there, that position should be less than equal to 5. Whenever this happening, so this is not happening. So since this is the 1, it gets me I is less than equal to 5. So this thing will not be incorporated if we don't increment I. So two dismerits, and you can also think about some other dismerits if you only take the part as if you don't increment I. But, so this is the algorithm of partition algorithm. We'll go back to the example and let's see how this kind of goes. Okay. Now in this example, let's start with the part where this is A. So this is the matrix A. This is 1, 2, 3, 4, 5, 6, 7. Here what? I is equal to 0, j is equal to 1, m is equal to 1, n is equal to 7. So here I is somewhere 0 and j was here. Okay. Okay. Now when j, now as I said, this is a of n equal to x. X I am taking. Okay. So x is equal to 7. And now I is equal to m minus 1. So m is 1. So I is, that's why I is equal to 0. Now j equal to m to n minus 1. Now from here it will run till here, till the first part. Now first it will check 6 and 7, whether since j is here, if 6 is less than 7, then this get interchanged. So now what will happen, we have an array here which is 6, 8, 3, 5, 2, 9, 7. Here it will have I, since it will get in I equal to 1, so now I equal to 1, and this gets interchange, aij interchange, so both remain the same position itself. Now whenever I is there, SS, this part is be less than 7, so till now 6 is less than 7, and after this j equal to 2. Now here we have j comes to here, 8 is greater than 7, 6 is greater than 6 is less than 7, this is 2 that we have done. Now 8 is less than 7, This is not true. So J will just move forward. J will move down to here. But now 3 is less than 7. This is true. Again an array will be made down. Now 6, 8, okay, 3, 5, 2, 9, 7. I will get incremented. I comes down to here. J is here. And these two particular positions get swept. 8 and 3. So this particular position after swapping, it will go as 3 and 8. So see, if every I value whatever taking is less than equal to 7. Okay. Now J will move forward. After doing this, J will move forward. This comes to J. Now 5 is less than 7. Again that is true. Now what will happen? For this particular part, J gets incremented. J gets incremented and this 2 right now gets swept. Okay. When this 2 gets swept, what will happen? 5 and 8 get interchanged. So 5 and 8 get interchanged. And J move forward after doing this. J move forward. Now 2 is less than 7. This is also true. Now 2 is less than 7. Again I will get incremented. I will get incremented. Now this 2 will get swept. When this 2 gets swept, 2 and 8. This 2 gets swept. Now 2 and 8. And J will get incremented. J will get incremented. As you see, for I, at every position when you swap this, every value from I to left part is less than equal to 7. Now 9 is less than 7. This is not true. And this is not true. Now this get terminated. Now this for loop terminated. And I, now what will happen? Interchange will happen. Interchange between what? If you see carefully this part, it is over I plus 1. Now what is I? I is actually 1, 2, 3, 4. I is actually 4. So interchange between A5 and AN. AN means here A7. So from this there will interchange will happen. Interchange between this and this. So at the end what you will get? You will get an array of 6, 3, 5, 2, I put this as 9, and this is 8, and this is what we got as 7. So if you look carefully again, this is all the elements which are less than 7 at the left side, and which is all the elements are greater than 7. And now in this example, the right side also not get sorted. Even the left side was not sorted previously, now the right side is also not sorted. So, but after demonetization, we'll get this particular part. And what will return? Return I plus 1. Since now I will just plus it, but now we'll actually return I was 4. Now I will become 5. Now this value will take as I equal to 5. This get returned. I equal to 5, we return down. So this is the question. So next time what we will do, we'll take this particular part and take this particular part. Then actually we have an array and this is the whole thing. Then we find out this particular part, then we call this. Then we again, maybe this particular part we again got. So we'll call this, we call this. So recursively we the divide and conquer, do we divide, then we call this, so we call this particular part. So recursively we'll call, divide and call it. But one thing is sure, whenever we take that particular element, again I'm saying this particular element that we are taking down as 7, this is known as pivot, but this is not the case. We can take any of the first, last and the middle of it. But whatever pivot element we are taking after running this partition algorithm, it will come down into the position where every element which has less than 7 will come down to the left hand side, and every element which is greater than 7 will come down to the right hand side part of it. This is the core idea of it. Now, before moving to the quick sort, let's have the overall analysis of this particular algorithm. There is no extra space associated with it. There is a constant amount of space that we can take down. So this is an in-place algorithm because only I is the one which is taking down. Apart from that, there is nothing other part. Only I is there. Apart from other thing, all setting are constant. So we J and M they all are constant, so depending on the area. So it is in-place algorithm. And secondly, is the time complexity required is that J needs to move from the first to the n minus 1 element. So the time complexity for the uh, partition algorithm it will take an order of n time, big O of n time to complete. So this is the one part that needed to be known. Okay. Then let's go to the partition algorithm of it. Okay. Just save it. Talk about this one. So here, what we completed, we have completed. Uh, we have completed the partition part of it. Now we'll move forward to the other recursive algorithms that are there. So we have completed this partition part, and for that, z is actually equal to 5. Yeah. Now we'll take that part, the same example, and let's see how this goes on. Okay. Marshall. This is the quick sort that we are defining. And you may seem like this is quite similar with the quick sort, but one thing you will find, there are some properties associated with quick sort, when to use quick sort, depending on how many numbers are there, you will whether apply quick sort, whether you must sort. So we'll discuss time complexity later on, then you can decide which particular algorithm to choose. Okay. Now let's have an example of it and let's see how it goes on. Let's take the previous example itself, 6835297. So 6, 8, 3, 5297. 5297. Okay, this is what we have taken. Okay, now here A we know, A we passed, M we passed, N we passed. Now since we have run this whole algorithm once, we have got an output from that. We got an output from that. This array will get changed. So remember, this array will also get changed. After running this, what we have got? We got 6352, 6352. We got 7, and we got 9 and 8. Okay, and this that we got it. So we write, let's say we write it in some other order to understand more clearly. Okay, I'll move this part to here. I need this space. I need this space to actually walk around. So that's why I just move it to here. 5297. Okay, and what we got? We got 6352798. Okay, we got this. Since in a merge sort we draw some kind of tree, let's start with drawing a tree here. We'll make it, I'll just quick sort as quick sort of it and actually take an array of 1 and then it is 1, 2, 3, 4, 5, 6, 7. Size of 1 to 7 is taken. This 1 is less than 7, here 1 is less than 7, so this gets over. Here we get a partition P which send an array of 1 to 7. This we have sent down. And then we cannot execute this too. We have to wait for this particular part to over. Previously in Marshall we have written this, but here we cannot write what argument need to pass. One argument we know is 1, but what is the next argument? So here also one argument we know, that is the n part 7, but what is the other argument will pass? We have seen z is equal to 5, as they have passed down in the previous one. Z, this is the one. What is this? 1, 2, 3, 4, 5. So z is equal to 5. Here they have passed down, return I plus 1. Now we know z is equal to 5. Now hence z is equal to 5, z minus 1, which is actually 5, 4. And here z plus 1, 6 and 7. That means this particular position and this particular part has been called down. Okay. Now here we will again have this function call. Now here they have a partition where it will be have 1 to 4. And then have the quick sort. We need to wait what we need to put down here, which we know we can write. We know 4 here, it will be here, and this will be 1. So we need to wait for the other argument that will pass. So let's see how this comes down. If we have this 1 to 4, 1, 2, 3, 4. So 6, 3, 5, 2. Okay. Then this is I equal to 0, j is here. Since 6 is not equal to 5, so 6 is not less than 5, so j will be just incremented to here. 3 is not less than 5, then again j will be incremented to the next one. J will move here. 5 also not less than 2, so again it will halt because j will move from this part to this part. Then there will be interchange between these two, I equal I to I plus 1 and this 2. So 2 will come here and 6 will come here. Okay, and it will return what? Z as 1. So this is what it will return, and Z as 1 because I now move as 1. Since it has got 1, it has got a Z value of 1, but then it will do a Z 1, so 1 minus 1, so 1 is 0, and there is 2. So it will be called on this and this part. So this is over. Now 1 and 0. Now you 2, 3, 5, 6, right? I just make it here. 2, 3, 5, 6. Yeah. Now 1 is m is here. This is m. This is n. M is not less than n, so this will not execute. This will again run. When this will get run, so partition will be called on 2 and 4. So this will have been called. So for this part, we have this 3, 5, 6. So 2, 3, 4. Again, j is I equal to 0, j equal to 1. 3 is not less than 6, so simply j will get incremented. 5 not less than 6, so simply j will halt here. Then I j will halt here. Then I gets incremented. So I gets incremented. I equal to 1, and there is a change. So what is there? Interchange from AI and AN. So it will still remain this 356 etc. So what it will return? It will return as there is no change because 356 is there. There is no change. I moves here. Interchange if 3 means 3. So I will be here 2 means this indexes will get returned out of it. So this is a quick sort again here, and again there is a quick sort from here. So for the quick sort, what it will call, one thing we know, there is 2 and there is 4. Okay, since this is this, so we return here z is equal to actually 2. So 2 minus 1 is 1, and here 2 plus 1 is 3 and 4. 3 and 4. Sorry, 3 and 4. Since again m is not less than n, so this will terminate and this will execute. Now this will again have two parts, 3, 5, 6. No? This is a main array that has been there, so 5 and 6 has been passed. So from here, if we just took on, so this will be part, there will be 3 parts, partition will be called 3 and 4. So if 3 and 4, 5 and 6 means 5 and 6. If I is here, j will be just run for one time, 5 is not equal to 6. Since 5 is not equal to 6, I will get incremented. I will get incremented here. Yeah, I will get incremented and the change will be not there, and there's a 5. So apparently, what it will send, it is here 5 and 6, so z will be 5. So 3 and 4, right? Oh, sorry, yeah. 3 and 4, this is 3, this is 4. Since it is 1, 2, 3, 4, this is 3 and 4. 3 and 4. So it will return z equal to 3. So quick sort of 3, 2 and quick sort of 3, it's 4, 4, 4, 4. Okay, yeah, 4, 4. So once 3 is less than, this is not true, this is not true, this is terminate, this gets over, this gets over, so this gets over. So when 1 to 4 is there, this is the last part we are going to get. So if we just this part from here, this is the last part we are getting 2, 3, 5, 6. So from this, what we get 2, 3, 5 and 6. This is what we got. Now from here also we get 6 and 7. So 6 and 7 means this and this. So you can see clearly if 6 and 7 is there, 9 is greater than 7, so this will terminate and I will just move forward and this 7 and 9 get replaced. After getting 7 and 9, this actually terminates, so we can have one more layer partition. It's been called 6 and 7, and there is some quick sort that has been called. Just do it one and you'll get to know the 7 and 9 will get changed from this particular part of it. So when 7 and yeah, from this part to this part, so 9 and 8. So from this part we get sorted 2, 3, 5, 6. This part is sorted as 8, 9, 7 is already sorted. So this particular whole array we got sorted part of it. Or just try to do for this particular part. I just not shown for this. Try to do for table because there are two parts. It is similar with what we have done for 3 and 4. But try to do it out for this. So that part we need to be carefully see about this. So how this goes. So algorithm starts with this. It starts with 1 and 7. It starts with 1 and 7 of partition sends. It sends in particular position. This particular position we have done this where we have included this particular part of sending. And then what we have done, we get z equal to here z we have done get as 5. So here we have got z is equal to 5 we have got. So now quicksort has been called. So quicksort has been called from a to z minus 1 4, and here z equals 6 to 7. So that's how we got this. Now we have to wait. So the main thing is that after partition has been called, we cannot say about this particular 6 and 4 until unless this is not over. So we have to wait for this. Then we have to call again the partitions in the recursive type of algorithm. We have to call partition from 1 to 4. 1 to 4 has been called, means from this to this side has been called. Now from 1 to 4 has been called. From this part we get to know that everything is there. So 5 and 6 will actually get changed. 5 comes here, this part gets changed. So this how things are going. Z equal to 1. Then this we got z equal to 1 from this. So 1 minus is 0 and 1 plus 1 is 2. M is not equal to n. So this condition is not satisfied, so this gets terminated. From 10 2 and 4 is there. From 2 and 4 we get to know about this to this part we are going to do. From this to this part we have 2 and 4. From this we get to know z equal to 2. Then we, since z equal to 2, 2 minus 1 is 1 and 2 plus 1 is 3. Since again m is not equal to n, this is not terminated 3 and 4. For this we just have two values, so we done this. We got the positions as 3, so we got the position as 3. So 3 minus 1 is terminated and 3 plus 1 is 4. So this is not terminated and this is not happening, so this gets over, this gets over. So I finally get 1 to 4, this part is all sorted down. And similarly we'll do for this part and we'll get to know the 7 and 8 and this is 7, so 8 and 9 will get from this. I hope this is clear to all of you. This is just a simple algorithm. You just need to take a pen and paper kind of thing and do this false order algorithm of time. Anyways, you're going to code this and it will run smoothly, but for your way how the flow is going, we need to know, because in Python or any other language, just need quick shot and everything comes out ready-made to you. But if, to be the core part of it, to know how things are going from which to which, take a simple example, take 1 2 3 5 array or numbers, you take it down any random numbers and try to apply your concept that you have learned, whether it is matching or not for this particular part. Okay, we discuss some, let's talk about some kind of properties associated with this particular part of it. So for the properties side, now we talk about the last point merge sort. There is a recursive tree we talked about some recursive tree, right? So let's move this out. Okay, yeah, we talked about some recursive tree. So what the recursive tree is, that how many, it is a function call. So when a function is called, some memory requirement is there. So whenever you call a function, there is something in memory need to be stored. So why we need a memory? First of all, let's say when you are calling quicksort of 1 and 4, it will wait till until then this particular last step is not completed. Until the last step is not completed, we need to wait. So this will take some memory to consume. This should take some memory to consume on that one side. Also, there is a quicksort of this, and it will wait for this output, but this will cannot execute, so it will take some memory. So every function call will take some memory. If you think about this, this cannot terminate until this cannot terminate it. The last function not terminated, this is not terminated out of. So there is some dependency. So there is some, when you talk about recursive, there is some memory requirement when you have too many function call also. Now we can think them as a stack. As we talked about, we can think them as a stack and we put them as a stack part of it. Now in stack part, we can push and out. So let's say this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, this is 14 talked about. We can push 1, we can push 2, then we push 3, then 3 finishes, then we push 4, then we 4 finishes, then we push 5, then we put 7, 6, 6 finishes, then we put 7, 7 finishes, then we put 8. Once 8 finishes, when 8 is there, so we can push now 9, 9 finishes we push 10, 10 finishes we push 11, 11 completed, 8 is popped out, 50 is popped out, 2 is popped out, then there is 12, then there is 13, then there is 14. So 14 popped out, 13, sorry, 14 will not be here, 14 will be actually here. Since 13 gets over, then 14 comes out. So 13 gets popped out, 14 gets popped out, 12 gets popped out. Actually, if this is I termed as 0, this is 0, so 0 gets popped out. So we can see there's, even though there are 14 function calls, but the memory requirement is what? For the one, this is, let's say this is 1, 2, 3, 4, 5, 6. This is 6. How we get to know? If we see about the length of this particular one, there is a particular length of this particular tree. So as we talked about previously, merge sort, this also depends on the length of the particular tree. So I will talk in some other video how we can get length of a particular tree, but basically we take as log n. So order of log n times it generally happens. So depending on the depth of the tree, we get a number of levels as to the depth of the tree itself. So here we have 1, 2, 3, 4 part. So if we have 16, that's how we get the number of levels associated with this. So we get log of n part and we get the number of levels associated. 7 if log of n they somehow come around to that particular part, etc. So that many number of requirements we have in the stack part itself. So that is number of levels associated with it. Okay. This is the quick sort that we talked about. This is what the partition algorithm we talked about. Now let's lastly talk about, we have talked about the properties initially, part of it. We talked about the in-place algorithm. We talked about recursive divide and conquer. That part we talked about initial slide itself. So this is the recursive algorithm, and we talked about this. Now at the time complexity, for the time complexity with this particular algorithm. Let's say in the base case, what should happen if we have Tn, this is divided equally, Tn by 2 and Tn by 2. This is the base thing that it could happen. Then again Tn by 4 and Tn by 4. This is the best thing it could happen if we divide this particular part. So we just inspect this in two property aspect, the base case and the worst case. So the base case, what will happen? Okay, I will just move to the complexity. That's just part of it. Okay. Okay, here itself we talked about the time complexity. Okay. Now initially we talked about the base class time complexity. Let's say. What the quick sort. Okay. Okay. For the base case, let's say it takes an order of n time. The partition will take order of n time. We discussed this J part at the time of discussing the partition algorithm. And as I said, for the base case, it divides them into equal halves, Tn by 2 and Tn by 2. It happens in the base case time. So this will take Tn by 2 amount of time, and this will also take Tn by 2 amount of time. So if we write the whole equation part of it, Tn order of write this in 2 into T of n by 2, and we have order of n times. And if we apply the Master's theorem, we discussed shortly about Master's theorem. In a shortcut to find time complexity, it will be n log n. This is how the time complexity will be there for the base case. For the base case, and base case what? This is the best thing will happen. It divide the array in both part. Divide the array in both part. In the sense, if we have an array and z is equally the middle part of it. If we have 10, z gets at 5. So this is the base case if we have. What's the worst case time complexity of it? When I say the base case, now what kind of situation it can happen that is not the base case of it. So let's first discuss what, let's give an example of it. Then we can get to know, acha, this is the base case and this is the worst case of it. So if we take an array which is already sorted, okay, if we take an array which is already sorted, then what do you think? Whether it is a base case or it is a worst case kind of thing. Let's take an example. Let's say if we took in 1, 2, 3, 4, 5. If we take an array which is already sorted, let's say this is the pivot element we are taking. After everything, what will happen? Pivot will remain in the same position. If you take 1 to 5, 2 to 5, 3 to 5, 4 to 5, it does not change this. Pivot will remain in the pivot position itself. Because I will just move from this. Since it remains there, what will happen? T n minus n elements we have to do the again the quick sort itself. And this is not done. We have to do this part. So for this we are taking T of n time. Partition anyways it will take order of n time because it will go for J1 to n. This, let's say it's happened on, we get the element as 5, so this we got as Tn minus 1, and for this it's there is not happening because it's already sorted, so it gets 0 part of it. So the final part will get T of n is equal to T of n minus 1 plus order of n times. This we will get. Right. And if you apply the back substitution method to solve this, you will get to know their time complexity is order of n squared actually to solve this particular one. So it is the worst case possible whenever take a pivot element and pivot element is already sorted. So it's a waste of computation that we are performing to this because there is no change of positions of it. Since everything is already sorted. Since everything is already sorted, then why we are applying quicksort of it? So that's how the partition. If we have a, let's say if you have 10,000 elements of it and you apply the particular part of quicksort of it, you take the last element and you found that these are already sorted. So this becomes difficult at that particular moment of time. So that's how there is some analysis we need to do. So this is the time complexity, worst case and a base case. In the merge sort, we discuss merge sort is always at the n log n, but these are two different cases of the quick sort part of it. So these things we have learned. We have learned about the algorithmic, the space and time complexity of it in the worst case and the base case. We took an example. We can draw this type of graph to actually find out how many memory requirements are there, how the flow is going down, at which particular point of time, which is the particular output. This kind of tree you can draw it down. You can take the partition algorithm, and one example we have done another example here of showing from any how partition algorithm generally works, step by step procedure of from this part j equal to 2, j equal to 3, j equal to 4, 5, how j changes, and at the end what happens, what interchanges is going to do, that we have got. And we talked about some kind of memory requirements also in that particular slide itself. Then we have started with this partition algorithm. We talked about the other one. We talked about the algorithm. Then we talked about what is it is a divide and conquer part. It is a recursive algorithm that we talk because it's a function call associated with it. So these are some properties of in place divide and conquer recursive arguments. And these are defined things that we have discussed in this one. I hope you have liked this particular video. If you have any questions, any doubt, you can drop a message in the comment box itself. I will try to answer the best possible part I can answer in the comment box itself. And that's it. We will come again with some another topic in another video. Thank you.